Relative homology. In algebraic topology, a branch of mathematics, the singular homology of a topological space relative to a subspace is a construction in singular homology for pairs of spaces. The relative homology is useful and important in several ways. Intuitively, it helps determine what part of an absolute homology group comes from which subspace. Definition. Given a subspace X, one may form this short exact sequence: 0 right arrow C, a right arrow C, X right arrow C, X slash C, a right arrow 0. Where Cx denotes the singular chains on the space X, the boundary map on Cx descends to C and therefore induces a boundary map delta and the quotient. If we denote this quotient by Cnx equals Cnx slash Cnr, we then have a complex $C dots backslash long right arrow Cnx a backslash X right arrow backslash partial NC n minus 1x a backslash long right arrow backslash C dots $. By definition, the Th relative homology group of the pair of spaces X is Hnx equals cr delta n slash m delta n plus 1. One says that relative homology is given by the relative cycles, chains whose boundaries are chains on a modulo the relative boundaries, chains that are homologous to a chain on a i.e. chains that would be boundaries modulo again. Properties. The above short exact sequences specifying the relative chain groups gives rise to a chain complex of short exact sequences. An application of the snake lemma then yields a long exact sequence. $$ C dos backslash to H and a backslash stackle I asterisk backslash to H and X backslash stackle G asterisk backslash to H and X a backslash stackle backslash partial backslash to H and minus 1 a backslash to backslash C dots $. The connecting map delta takes a relative cycle, representing a homology class in H and X, add to its boundary which is a cycle in a. It follows that H and X, where X0 is a point and X is the nth reduced homology group of X. In other words, HIX X0 equals HIX for all I0. When I equals 0, H0x, X0 is the free module of one rank less than H0x. The connected component containing X0 becomes trivial in relative homology. The excision theorem says that removing a sufficiently nice subset Z leaves the relative homology groups H and X unchanged. Using the long exact sequence of pairs and the excision theorem, one can show that H and X is the same as the nth reduced homology groups of the quotient space X slash A. Relative homology readily extends to the triple X, Y, C for Z, Y, X. One can define the Euler characteristic for a pair YX by $backslash j x y equals backslash sum j equals 0 n minus 1 j backslash operator name rank h j x y. $. The exactness of the sequence implies that the Euler characteristic is additive, i.e. if z y x, one has chi x z equals chi x y plus chi y z. Local homology. The nth local homology group of a space X to point X, denoted Hn xx, is defined to be the relative homology group Hn x backslash x. Informally, this is the local homology of X close to X. Local homology of the cone Cx at the origin. One easy example of local homology is calculating the local homology of the cone topology of a space at the origin of the cone. Recall that the cone is defined as the quotient space Cx equals x times s slash x times 0, where x times 0 has the subspace topology. Then, the origin x0 equals 0 is the equivalence class of point. Using the intuition that the local homology group H asterisk xcx of Cx at x0 captures the homology of Cx near the origin, we should expect this as the homology of H asterisk x and Cx backslash x is a homotopy retract to x. Computing the local homology can then be done using the long exact sequence in homology. $backslash begin a line backslash to an H and Cx backslash set minus backslash x0 backslash to H and Cx backslash to H and backslash x0 backslash Cx backslash to an H n minus 1 Cx backslash set minus backslash x0 backslash to H n minus 1 Cx backslash to H n minus 1 backslash x0 backslash Cx. Backslash underline $. Because the cone of a space is contractible, the middle homology groups are all 0, giving the isomorphism. $backslash begin a line H and backslash x0 backslash Cx and backslash con H n minus 1 Cx backslash set minus backslash x0 backslash and backslash con H n minus 1 x backslash and the line $, since Cx backslash x is contractible to x. In algebraic geometry. Note the previous construction can be proven in algebraic geometry using the affine cone of a projective variety X using local cohomology. Local homology of a point on a smooth manifold. Another computation for local homology can be computed on a point P of a manifold M. Then, let Calvin be a compact neighborhood of P isomorphic to close this $backslash math D n equals backslash x backslash and backslash r n x backslash lec 1 backslash $, and let U equals m backslash k. Using the excision theorem, there is an isomorphism of relative homology groups. $backslash begin a line H n m backslash set minus backslash P backslash and backslash con H n m backslash set minus U m backslash set minus U backslash gut backslash P backslash and equals H and k backslash set minus backslash P backslash and a line $. Hence the local homology of a point reduces to the local homology of a point in a closed ball letter 1 d5 3 bn. Because of the homotopy equivalence. Letter 1 d5 3 bn backslash 0 sm minus 1 and the fact $H k backslash math D n backslash con backslash begin cases backslash D and k equals 0 backslash 0 and k x0 backslash end case is $, the only non-trivial part of the non-exact sequence of the pair letter 1 d5 3b, letter 1 d5 3b backslash 0 is 0 right arrow hn 0, letter 1 d5 3b in right arrow hn minus 1 sm minus 1 right arrow 0, hence the only non-zero local homology group is hn 0, letter 1 d5 3b n. Functoriality. Just as in absolute homology, continuous maps between spaces induce homomorphisms between relative homology groups. In fact, this map is exactly the induced map on homology groups, but it descends to the quotient. Let x and y be pairs of spaces such that x and by, and let f, x right arrow y be a continuous map. Then there is an induced map f hash cnx right arrow cny on the absolute chain groups. If f a b, then f hash cn a cnb. Let $begin a line backslash pi x and cnx backslash long right arrow cnx slash cn a backslash pi y and cny backslash long right arrow cny slash cnb backslash and a line dollar be the natural projections which take elements to their equivalence classes in the quotient groups. Then the map pi y f hash cnx right arrow cny slash cnb is a group homomorphism. Since f hash cn a cnb equals car pi y, this map descends to the quotient, inducing a well-defined map phi cnx slash cn a right arrow cny slash cnb such that the following diagram commutes. Chain maps induce homomorphisms between homology groups, so f induces a map f asterisk hnx or right arrow hny, b and the relative homology groups. Examples. One important use of relative homology is the computation of the homology groups with quotient spaces x slash a. In the case that is a subspace of x fulfilling the mild regularity condition that there exists a neighborhood of it that is a deformation of a tract, then the group nx slash is isomorphic to hnx a. We can immediately use this fact to compute the homology of a sphere. We can realize Sn as the quotient of an n disk by its boundary, that is Sn equals dn slash Sn minus 1. Applying the exact sequence of relative homology gives the following: right arrow n dn right arrow hn dn Sn minus 1 right arrow n minus 1 Sn minus 1 right arrow n minus 1 dn right arrow. Because the disk is contractible, we know its reduced homology groups vanish in all dimensions, so the above sequence collapses to the short exact sequence. 0 right arrow hn dn Sn minus 1 right arrow n minus 1 Sn minus 1 right arrow 0. Therefore, we get isomorphisms hn dn Sn minus 1 n minus 1 Sn minus 1. We can now proceed by induction to show that $hn dn Sn minus 1 backslash con backslash c $. Now, because Sn minus 1 is the deformation retract of a suitable neighborhood of itself in Dn, we get the $hn dn Sn minus 1 backslash con backslash tilde hn Sn backslash con backslash c $. Another insightful geometric example is given by the relative homology of $x equals backslash complex asterisk d equals backslash 1 backslash alpha backslash $, where alpha not equal to 0, 1. Then we can use the non-exact sequence. $, begin a line 0 and backslash to h1 d backslash to h1x backslash to h1x d backslash and backslash to h0 d backslash to h0 x backslash to h0x d backslash end line equals backslash begin a line 0 and backslash to 0 backslash c backslash to h1x d backslash and backslash to backslash c backslash whole plus 2 backslash c backslash to 0 backslash end line $. Using exactness of the sequence, we can see that h1x d contains a loop sigma counterclockwise around the origin. Since the coconut of $phi backslash colon backslash d backslash to h1x d fits into the exact sequence. $0 backslash to backslash operator name coca backslash phi backslash to backslash c backslash r plus 2 backslash c backslash to 0 $. It must be isomorphic to $backslash c $. One generator for the coconut is the one chain since its boundary map is delta equals minus